Hello, Ravi sir.
Yes, ma'am. Morning.
VC ma'am வந்திருக்காங்களா லைவ்ல?
என்ன மேம்?
VC ma'am வந்திருக்காங்களா சார்?
இன்னும் வரலைங்க மேம். வந்துட்டாங்களா?
இல்ல அதான் உங்ககிட்ட கேக்குறேன்.
15 தான் ஜாயின் பண்ண சொல்லியிருக்கேன் மேம்.
ஓகே சார், ஓகே சார்.
10:15 வந்துருவாங்க.
ஓகே ஓகே ஓகே.
சார் வந்துட்டாங்களா? ரவிச்சந்திரன் சார்?
வந்துட்டாங்க சார்.
சார் வந்துட்டாங்களா?
வந்தாச்சு.
ஓகே ஓகே.
ரவி சார்.
மேம்.
மேம் வந்தா ஒரு 2 minutes முன்னாடி வந்தாதான் co-host மாத்த முடியும். மேம் ஆல ஆடியோ வீடியோ ஷேர் பண்ண முடியும். நம்ம ஸ்டார்ட் பண்ண அப்புறமா அவங்க எதுல வருவாங்கன்னு தெரியல.
மேம். அந்த மேம்.
சொல்லுங்க சார்.
கம்பெனி பார்ட்டிசிபென்ட்ஸ் அப்படின்னு கேட்டுக்கிறாங்க விசி மேம். மொத்தம் இதுவரை எத்தனை பேர்? 237 யூடியூப் லெவல்ல பேர் மொத்தம்?
இதுல ஒரு 241 ஆட் ஆயிட்டே இருக்காங்க. யூடியூப்ல வந்து we have around 10-15 வாட்சிங் சார்.
எவ்வளோ மேம்?
ஆட் ஆயிட்டு இருக்காங்க ஒரு 10 பார்ட்டிசிபென்ட்ஸ்க்கு கிட்ட.
ஓகே.
எஸ் சார்.
டோட்டல் நேற்று வரல எவ்வளவு கிராஸ் ஆச்சு?
1350 கிட்ட வந்துச்சு சார். So it's almost time. Shall we start?
மேம் வந்துட்டேன் மேம்.
எஸ் சார்.
மேடம் வந்துட்டாங்களான்னு பாருங்க.
வந்துட்டாங்க சார். மேம் வந்துட்டாங்க.
மேடம் வந்துட்டாங்களா?
யா.
மார்னிங் மேம்.
மார்னிங் மேம்.
மார்னிங் மேம்.
மேம் சார் வந்துட்டாங்களா?
வந்துட்டாங்களா மேடம்? மேம் சொல்றாங்க.
சசிபிரபா மேம்.
டைம்ல இருக்காங்க சொல்லுங்க சார்.
யா சசிபிரபா மேம் தெரியல மேம். ஆனந்தி மேம்.
எஸ் மேம்.
யா ப்ளீஸ் மேம்.
மேம் சார் வந்துட்டாங்களா ரவிச்சந்திரன் சார்?
யா இருக்காங்க சார்.
அப்ப ஸ்டார்ட் பண்ணிடலாம் மேம்.
ரவிச்சந்திரன் சார். சார். யா எஸ் சார்.
Sir.
Sir.
Yes.
Yes sir. Yes sir. Morning sir.
Good morning. Good morning.
Morning, madam. Morning.
Good morning.
Good morning ma'am.
Good
Morning. Shall we start ma'am?
Yes. Yes. You can start.
Yes sir. Thank you.
Okay.
Anita ma'am, video ma'am. Good morning. Anita ma'am, video. Okay ma'am, I'll start up now. Good morning everybody. A pleasant welcome on behalf of the organizers, Professor M. Sundareshwari, Dean, School of Science and Humanities, Professor S. Ravichandran, Head of Department of Physics, and the conveners, Dr. S. Anandi, Dr. S. Murugeshan sir, and myself, Anita, from the Department of Physics, wish a warm and hearty welcome to all the participants on this inauguration of the one-week online workshop on Material Technology Advancements in Current Scenario, MTACS 2020, organized by the Department of Physics, School of Science and Humanities, Satyabama Institute of Science and Technology. I extend a warm welcome to Dr. T. Sasiprabha, Vice Chancellor, Satyabama Institute of Science and Technology. It's an honor to have your presence in this platform, ma'am. Welcome, ma'am.
Thank you. Thank you.
It's a privilege for being connected with you in this virtual platform, ma'am. I put forth my wholehearted welcome to our guest of honor, Professor K. Ravichandran, Director, Institute of Distant Education, University of Madras, for his esteemed presence here. Welcome, sir.
Welcome, sir. Welcome, sir.
My special and heartful welcome to our Dean, Dr. M. Sundareshwari, and to all the participants for being solid supporters. I also extend my special welcome to all the participants who have been sailing with us since a previous FTP conducted between 24th to 30th June 2020. Thank you all for joining us here with us again. Our team feels privileged to inform you that we have more than 1,300 participants registered around the globe from China, South Korea, Japan, United Kingdom, Dubai, Bhutan, and covering almost all states and union territories in India, including Andhra Pradesh, Arunachal Pradesh, Bihar, Chhattisgarh, Gujarat, Haryana, Himachal Pradesh, Jharkhand, Karnataka, Kerala, Madhya Pradesh, Maharashtra, Odisha, Punjab, Rajasthan, Tamil Nadu, Telangana, Uttarakhand, Uttar Pradesh, West Bengal, and Pondicherry, Jammu Kashmir, and New Delhi. Thank you all for joining here with us. As we know, knowledge has a beginning but no end. Knowledge is like a garden. If it is not cultivated, it cannot be harvested. Moreover, how much knowledge you gain depends on your willingness to learn. Furthermore, it is knowledge which you should come to. It is not who should seek it. It is you should seek the knowledge. Of course, sharing occurs when people are genuinely interested in helping one another develop new capacities for action. It is about creating learning processes. And definitely there is no wealth like knowledge, no poverty like ignorance, as Buddha says. Yes, participants, in this workshop, we have lectures to be delivered by expert faculty members and professionals from reputed organizations around the world to provide insight and future scope of material technology advancements in current scenario. To say a few words about our university, Satyabama Institute of Science and Technology, a Christian minority institution, formerly known as Satyabama Engineering College, was established in 1987 by Colonel Dr. JPR. It is a premier institute imparting knowledge in the area of engineering, science, technology, and education. Satyabama Institute of Science and Technology, with the blessings of founder Colonel Dr. JPR, have strengthened the development activities by bearing fruits of research for betterment of the society. Our Chancellor, Dr. Marie-Gina Johnson, President Dr. Mary Johnson, endows with the necessary thrust in all development activities of our university. Our Vice Chancellor, Dr. T. Sasiprabha, Pro Vice Chancellors, Dr. E. Logashanmugam and Dr. Wilson Arunai, Registrar, Dr. S.S. Rao, and the Controller of Examinations, Dr. S. Igni Sebastian Prabhu, makes available the necessary support for the best endeavors. The Institute progress and contributions to the field of technical education for over 2 decades resulted in granting deemed university status on 16th July 2001. The university has been awarded as Category A University by the Ministry of Human Resource Development, Government of India, and accredited by NAC with Grade A in the year 2017, certified with DNV GL ISO 9001 standards, and offering exemplary education for the last 29 years. Untiring efforts of the management, staff, students, and positive academic privilege in the campus had made university to be ranked as second among private universities in Tamil Nadu by National Institutional Ranking Framework. University is also declared as one amongst the top 31 deemed universities by the Time Higher Education Ranking. We have written history, a special page in the history of space research on 22nd June 2016 with the launch of Satyabama SAT in association with ISRO. And about our department, the Department of Physics is an DST fifth sponsored department since 2015 to 20 with a funding of 74 lakhs and is one among the ST's established departments since the inception of the institution. The department is aiming to establish facilities for specialized area of research with assistance of funding agencies. The department has received 5 research grants from various government funding agencies such as DST, DRDO, and UGC, DAE. With this introduction, I now invite our Vice Chancellor, Dr. T. Sasiprabha, Satyabama Institute of Science and Technology, to give the presidential address.
Okay. Yes. So very good morning.
Very good morning, ma'am.
Yes, especially the HOD of Department of Physics, the Dean of School of Science and Humanities, and our guest of honor, Director of Institute of Distance Education, University of Madras, and all my dear participants. I heard that this FDP attracts more than 1,000 participants across the globe. It was good to see that this many number of response during this pandemic period. So how this academic community is utilizing this period effectively. Really, I am appreciating all the participants who are here in this FDP. It's a 7 days FDP. I hope because of all the speakers and the efficient conduct of the FDP by the department and the good speakers have attracted this many academicians on this virtual platform. I'm thanking the department and especially Dr. Ravichandran, HOD, supported by all his staff members and the Dean School of Science and Humanities and all my dear speakers for your acceptance to be a part of this FDP. And all the once again, I'm thanking all the participants across the globe. I hope this FDP will surely give you a lot of enlightenment in this field of material science. I'm very happy to say that Satyabama is proud to host this type of conferences or FDP on this very important topic, material science, because Satyabama has got a full-fledged facility to carry out the material science research activities, right from synthesis to characterization of materials. We have the high-tech instruments. It was used by almost all scholars throughout India. Even our government departments like ISRO, DRDO, DAE departments are also coming and utilizing facilities. So I request the participants, please look into our website, or you can, we have got a center website, Center for Nanoscience and Technology. So you can see the various facilities available there, how to approach us, everything was given in the website. You can always see, and you can utilize the facilities. We are ready to support all the research scholars who are working in this area of material science. Once again, I'm thanking all the participants, speakers, and our guest of honor, and our HOD Physics department for having organized this FDP on 7 days on this very, very important topic. Thank you.
Thank you, ma'am.
Thank you.
Thank you. Thank you, ma'am, for being with us and gracing this occasion.
Thank
Now
you
I
so much.
call upon our chief guest, Professor K. Ravichandran, Director, Institute of Distant Education, University of Madras, to give the inaugural address. Sir.
Most respected Vice Chancellor, Dr. T. Sasiprabha Madam, Professor Sundareshwari, Dean, Science and Humanities of Satyabama University, Professor Ravichandran, Head of the Department of Physics, and enthusiastic conveners, Dr. S. Ananthi, Dr. Anita Lett, and Dr. Murugesan, organizing committee members, participants, researchers, academicians, and my dear students. Very good morning. It's indeed a great pleasure for me to be part of this program. My pleasure becomes double since I am also working in the area of material science. Outwardly, I am in an administrative position, and Khaled may be knowing we have a couple of papers, good research papers in the area of material science. Really glad to be a participant for this. The topic is really a very interesting one, and I could able to see a huge gathering and nearly 1,000 participants. It's really a wonderful thing. I could say it is a blessing in disguise in the pandemic situation, especially for academicians like us. Previously, organizing such a huge workshop, it's really very, very tough because it involves a lot of logistic arrangements, finding participants, finding experts, and spending money, and managing all those things have become very hectic. Now it becomes
Easy.
really is little simpler,
Yes.
especially getting the experts across the world and getting participants across the world becomes very, very simple. So we should be thankful to the COVID in that sense, and especially the technological advancements we have. On coming to the topic, the development of materials technology advancement in current scenario, a wonderful, wonderful topic. And you have made a 1 week program, and really it is very, very amazing. The material science, you know very well, it is all these people are working in the material science. Material science is an interdisciplinary area of research which involves a combination of physics and chemistry, studying the physical and chemical properties of materials, developing newer materials and their application. It's a very, very important field because the development from Stone Age to the current situation, current age, it's all because of made possible because of the developments in the materials. The world is looking for a stronger, cheaper, more durable, eco-friendly, economic, and lighter, corrosion resistant, thermal resistant, abrasion resistant materials, functional materials which are being required right now. So the advancements in the material science and technology made it possible to go for these materials. So the developments has warranted the current developments warranted creating a newer materials which has been find widespread applications in various fields of not only in engineering, in general, it's various fields. You can say one of the most important application of newer materials, requirement of newer materials is biomaterial. It's a very good field or very fast growing field. So starting from stents, pacemakers, orthopedic implant materials, targeted duct delivery materials, sustained release materials, scaffolds. So all those things are possible now. We are using it now, and we are again looking for some more developments in these materials because of the technological developments available in the frontiers of material science. And similarly, the developments in ceramics, glasses, composites. So the ceramic glass composites, they have a very good thermal resistance, very good corrosion resistance, very good electrical resistance. So and they can withstand at very high temperature, and all those properties made possible to get a material which can be used for aerospace applications, automobile applications, electronic industries, and all. So this is again another area where the material science is contributed a lot. And as coming to the another facet is the engineering materials. Engineering materials means mostly engineering alloys. If you take engineering alloys, it may be an iron-based alloys, starting from steel to stainless steel to duplex steel. All those steels are possible by the combination of different alloying elements. And similarly, if you want some highly corrosion-resistant materials, you can go for nickel-based alloys. So various combinations of alloying elements to the nickel, giving a nickel-based alloys, and magnesium-based alloys, especially for nowadays the soluble implant materials, soluble biomaterials, which has been made possible by the use of magnesium-based alloys, and similarly aluminum-based alloys, which have been widely used for the aerospace application, and titanium-based alloys again for aerospace application, especially nuclear industry, disposal of waste materials, especially radioactive waste materials for 500 years or even more than that is possible now because of the availability of titanium and titanium-based alloys. So the engineering applications of these and all these alloys are really excellent. This is again another facet of the developments in material science, and the nanotechnology, nanomaterials, nano-functional materials, all those things, current development, recent development. So this is the smaller size, which gives a very high surface area. Strength to weight ratio is very high. The reactivity is very high, which improves varieties of functions, especially the functional materials. You can design a material, tune a material depending upon the requirement. So these developments has been very much useful in the area of electronics, in the area of so many areas, you can say. Basically, electronic industry is tapping the developments of the nanomaterial and all the other areas, in fact, coatings, alloys, even for treatment of effluents, absorption, all those functions has been made possible by the development of nanomaterials, which again, the material science is responsible for it. And so the electronic industry, biomedical industry, automobile industry, all those things, especially the graphene, carbon nanotubes, functionalized graphene, all those things are now possible. So this opened up newer avenues in the nanotechnology and especially the material science, like material science developments. And currently we may be thinking of about the integrating the material science developments along with artificial intelligence can get newer products. So maybe we are looking for such kind of things. So there's a current research going towards integration of the developments in the material science with artificial intelligence to get a product. Such a developments are possible. Not simply, it is not possible. Previously, when I am doing my research, what we have is only a metallurgical microscope. Now, nobody is using a metallurgical microscope. Now, we have so much of microscopic techniques, starting from scanning electron microscope, even scanning electron, different versions, transmission electron microscope, atomic force microscope. Similarly, since there are so many microscopic techniques are available, and spectroscopic techniques are advanced spectroscopic techniques are available. Maybe a couple of I went through the brochure. I see there are a lot of people going to speak about the lot of spectroscopic techniques, especially X-ray diffraction techniques, X-ray photoelectron spectroscopic techniques, large electron spectroscopic techniques. So all those kind of techniques are now currently available, and the facilities are available all over the world. And even in Satibaba University, they are having an excellent facilities of microscopic and spectroscopic techniques. And the recent developments in the electroanalytical techniques, especially sensors. The development of material science paved way for a lot of sensors, especially biosensors, even in the microscopic, nanoscopic materials can easily be analyzed using the sensor. That is also possible because of the developments in the material science and technology. Hence, so choosing such a topic is really, I am giving my heartfelt appreciations to the organizers and Satyabama University for coming up with such a wonderful topic for a workshop. So really worthwhile to have a workshop. My appreciations for the entire team, and hope all those participants, the huge number of participants, will definitely be benefited by the 1 week of interaction with the experts, the gamut of experts available with you. So please enjoy those time. And thank you very much. Thank you. Thanks a lot for giving me an opportunity to be a part of this program. Thank you very much. Thank you.
Thank you, sir. Thank you, sir, for embellishing us with your talk. Sir, being my PhD supervisor, I feel happy to deliver my thankfulness for gracing this occasion, sir. Thank you, sir.
Thank you.
Now I call upon our Head of Department of Physics, Professor Dr. S. Ravichandran, Satyabama Institute of Science and Technology, to confer the vote of thanks.
A pleasant very good morning to everyone. Gratitude is the mother of all virtues. So I would like to thank our founder, Chancellor, Colonel Dr. JPR. With his blessings, always the programs going on well. Next, I would render my sincere thanks to our Chancellor Ma'am, Dr. Mayuzina Johnson, for her confidence and trust that she has and in us always with us to bring the university to the #1 position. I would like to thank to our President Sir, Dr. Mary Johnson, who has motivated all the staff members by his encouraging words by and deeds. I would like to render my thanks to our Vice Chancellor Ma'am, Dr. Shashi Prabha, who is always an inspiring force for all of us and endeavor and for giving his consent and joining with us. Thank you, ma'am. And I would thank to our Professor Dr. Ravichandran, Director, Distance of Education, University of Madras, to joining us. Thank you, sir. I would thank to our Pro Vice Chancellor, sirs, for rendering their support to us. I would like to be grateful for our Registrar Sir, Dr. S.S. Rao, and Controller of Examination for guiding us in all of our endeavors. Next, I would like to thank to our opportunity to thank to all the deans and HODs for their valuable support and cooperation. And my sincere thanks to our Science and Humanities Dean, Dr. M. Sundareshwari, for his valuable suggestions and guidance. Finally, my sincere thanks to our organizing team and to all the organizers that for conducting the program successful. Once again, I welcome you all for the program to be successful. My special thanks to Dr. Anita and Dr. Anandi ma'am and Dr. Murugesan for a wonderful organization. Thank you, ma'am. Thank you very much.
Thank you, sir. Thank you, sir. Dear participants, I hope this workshop will definitely serve as a platform and provide a feed for your never-ending research thirst. So with this, we end up our inaugural session. Shall we start our next session, ma'am? Sir? We now proceed with our session today. We have with us Dr. Surendra Chandran, Associate Professor, Indian Institute of Technology, Kanpur, and here he is to impart his knowledge on the scope and potential of different phases of entropy for soft materials. Welcome, sir. Hello, sir.
Ma'am.
Yeah, so now should be all right?
Yes, sir. Yes, sir.
Yeah, okay. Thank you.
I now request Dr. S. Murugesan, sir, to introduce the speaker for today's session.
It's my pleasure to introduce then with the blessings of our founder chancellor, Dr. Colonel JPR sir, and also with the great support from our management, we have started conducting 7 days workshop on material technology, advancement in current scenario. I have immense pleasure in welcoming our today's guest speaker, Dr. Siva Surendra Chandran. He is currently working as assistant professor at the Department of Physics in Indian Institute of Technology, Kanpur. Prior to this, he carried out his postdoctoral research at the University of Freiburg and at the University of Tübingen for 6 years. He earned his MSc in 2008 at Material Science Anna University as a gold medalist and finished his PhD in 2014. Later on, he joined as UGC Meritorious Fellow in Soft Condensed Matter Physics at the Indian Institute of Science, Bangalore. His research focuses on understanding and controlling various non-equilibrium phenomena. That means that is glass transition, crystallization, aging, rheology, and wetting, de-wetting observed in polymers and colloids. To his credit, Sir has published 23 scientific articles in all high-impact journals like Nature Communications, Physical Review Letters, Macromolecules, Nanoscale, ACS Macro Letters, Soft Matter, and so on. He has also attracted funding from various agencies, including German Research Foundation. Sivasa has been a review of journals like Scientific Reports, Nature Publishing Group, this one belongs to. Applied Physics Letters, Journal of Applied Physics, Review of Scientific Instruments, and Journal of Applied Crystallography. Once again, I welcome you, sir, for 1 week workshop, this first day. Then I invite you to carry on the talk on your talk, sir. Thank you, sir. Thank you so much.
Okay, thank you. So shall I start with sharing the screen?
Yes, sir, please.
So do you see my screens now?
Yes, sir, it's clear. Giving your voice is audible.
Okay, fine, great. So thank you, Dr. Murugesan, for introducing me with the kind introduction. And I thank Dr. Anandi for inviting me into this seminar. It is indeed a great pleasure for me to speak with you all on the workshop Materials Technology Advancement in Current Scenario. So the speaker before me, the director of distance education, he gave a very detailed introduction to the various kinds of technology, the advancements which is currently existing in today's research. Today, instead of speaking about the technology, I would rather speak about science, a fundamental concept called entropy, and how the manifestation of such a fundamental concept could yield different materials, especially novel behavior, which in turn can give rise to new technologies, as I would show in the final part of my talk, right? And before getting into the talk, let me confess straight away here that this is not a research intensive talk. Rather, the idea is to introduce you to the concepts of entropy, and in doing so, I will be showing some of the recent research results as well, but with an idea of just to let you appreciate the different facets of entropy. On hearing entropy, you may on the first go think that, like, okay, we all have read about entropy and we have studied entropy, so what is new with that, right? So with this talk, I hope to convince you that entropy is still a topic of active discussion, and there are a lot of new technology and new properties of materials which can come by manipulating this fundamental concept called entropy in materials. So since our talk is going to be on entropy, it is rather a good idea to start with thermodynamics' second law, which has been instrumental in our understanding of entropy. So while the first law of thermodynamics have stated as that the energy should be conserved, the second law of thermodynamics have put a restriction on the direction of the flow of heat. Heat cannot spontaneously flow from cold to hot, right? And with such a simple definition, it is rather difficult to make progress. And that is when Rudolf Clausius has appeared into the picture. So what Rudolf Clausius has done is that he reformulated such a simple statement and revealed that there should exist a parameter called entropy, which for a closed system, that is a system which cannot exchange heat with its surroundings, that parameter entropy cannot decrease spontaneously. That is, entropy of a closed system never decreases, right? And this definition of entropy, this entropy, right? This parameter of entropy is basis of all thermodynamics which followed, starting from Gibbs looking at the phase coexistences to the Boltzmann search of the microscopic definition of entropy. So by the way, Clausius himself has never told what is the definition of entropy. He just introduced this parameter and said that this parameter can never decrease spontaneously. So what is the definition of entropy? Right? Thanks to Planck, Boltzmann, Gibbs, and Shannon, that there exist several definitions of entropy. However, the most common and the often used, especially in the student community, is the definition that entropy is defined as a measure of degree of disorderedness. And the question that I'm trying to raise here is, such a definition of entropy is enough to understand the various aspects and the various manifestations that it shows, right? To highlight my point, here I show you various processes, starting from the crystallization of colloids to diffusion of proteins in crowded atmospheres like in cells, and to an intriguing concept called autophobic dewetting, which basically means that materials of the exactly same nature can dislike each other, right? And also here I show you a microfiber, which I think you could now see that it pulls a load which is much heavier than the fiber by itself autonomously, right? Without any external forces, right? So now you may think that, like, why am I showing such apparently different processes in the same slide, right? If you have not guessed so far, then these are essentially the different phases of entropy that I'm trying to convince you with, that entropy can in principle give rise to so many such rich and different complex processes. To convey my point, I'll be following this outline of the talk. I'll start with rather an ironical subtopic, which is when entropy can favor order instead of disorder, right? That entropy can favor crystallization. And then I will go on to show you that entropy, if you could manipulate it in a proper way, then you could make materials of exactly the same chemical nature dislike each other, right? And finally, I will show also that if you could, have this entropy in stock for materials, like via processing or subjecting them to different fields, then in principle you could get behavior which are so novel that start questioning our intuitions, right? Okay, so entropy favoring crystallization, right? So we all know crystallization, that like is a process where a disordered liquid transforms into an ordered solid, right? We understand this via energy minimization. For example, here I've given you a free energy, which is defined via the internal energy minus the entropic part, right? So when the free energy minimizes, you get an ordered crystal. Now, from an entropic perspective, if you see, you're changing a liquid which is disordered into an ordered solid, which is you're going in the direction of a decrease of entropy. We just have now discussed that, like, second law of thermodynamics tells you that a process cannot form spontaneously where the entropy is going in the decreasing direction, right? So how do we understand this? So we understand this that during the crystallization, all molecules release heat to the surroundings and then forms the crystal. And this heat is a price that the system pays in order to go on a direction where the entropy is decreasing, right? So in order to go in a direction in a decrease of entropy, we have to pay an energetic price, right? And now, given this understanding, already in 1957, Alder and Wood came up with a very interesting hypothesis, a suggestion that, like, what if one thinks about a system where there is no energetic interactions, right? So then the free energy is essentially dominated by entropy, right? And now if one can create a system of that sort, so could we see crystallization, right? So for doing that, what Alder and Wood has done is, like, they introduce entities called hard spheres in their simulation, right? So hard spheres are nothing like but like as like steel balls that you can think of, but much smaller in size. And these have no interactions when they are well separated. And the moment they start touching each other, then of course the Coulombic repulsion will be huge, right? So when they are far from each other, the interaction energy is zero. They don't care whether there are neighboring particles or not, neighboring hard spheres or not. The moment they touch us, the interaction energy goes to infinity, right? That's how we define an hard sphere, and that's what they have used in this system. And now, as we just discussed, we could now create a system where the energetic interactions can be completely avoided, right? And now we have only entropy. And then the question that we were asking is, can such entities crystallize, right? Yes, indeed, in simulations, it shows that such hard sphere liquids can crystallize. That is, hard sphere disordered liquid can become crystals which are ordered. Now, remember that we have no energetic price to pay, and hence this becomes a kind of going against the second law of thermodynamics. So then how does this crystallization happen? How does this entropy spontaneously decrease, right? To address this question, I invoke two other gentlemen and heroes of the field, Ludwig Boltzmann and Josiah William Gibbs. So what these guys have done is come up with a microscopic definition of entropy, which you might have studied in your statistical physics courses, where entropy is defined simply via looking at the probability that a system exists in a given microstate multiplied by the logarithm of the same probability. And now then you take this quantity and you sum up over all the existing microstates and multiply that with the Boltzmann constant, then what you get is called entropy, right? So and this probability goes inversely with the number of microstates which are accessible. So in simple words, at a given energy, a system can have so many different microstates. Each microstates, as you know, are defined by the local parameters, and now this can occupy many microstates. And if you have larger number of microstates to be occupied, then the entropy is higher. If you have smaller number of microstates to be occupied at a given energy, then the entropy is low, right? So how do we understand our hard sphere crystallization using this? So what we could now clearly show, both via calculation and in computer simulations, is that these hard sphere liquids, they can not be arranged with as many ways as an hard sphere crystal can be arranged. So there are more ways in forming a crystal, hard sphere crystal than in forming a hard sphere liquid. Thus, from a microscopic definition of entropy, we are speaking about a liquid which has low entropy than the crystals, right? So the definition of degree of disorderness still holds, but we are now speaking about degree of disorderness at the microstate level, right? In a more microscopic level. So now the question that, I mean, when this was shown, this has created a lot of stir in the community at that time, right? Because this is going on a direction which you wouldn't expect. And then, calculations seem to indicate that crystals have higher entropy than liquids, especially in this case. And then people are asking, like, okay, what is this hard sphere something which can be experimentally possible? Can we make these hard spheres experimentally? Of course, you cannot make it with atoms. And the answer turns out to be that, like, you can in principle make them with colloids, right? So for those who don't know what colloids are particles which are often in the size range of a few micrometers to tens of nanometers, right? And which exhibit Brownian motion, right? So gravity can be forgotten, and this is just like, roaming around all throughout because of the imbalance of the momentums which are transferred by the surrounding medium. So essentially, these are very small particles which can just, like, roam around performing random walks, right? And with these simple systems, Pussy and Van Meegen in 1986, they came with a simple system, right? Like, so these are simple polymers based colloids, and their diameters are of the order of 600 nanometer. And they have dispersed these colloids in a solvent which is a mixture of decaline and carbon disulfide. And once they have mixed this and they have some polymers which are grafted, as I've shown you with the black lines here, these are center PMMA colloids, and on top of that you have polymers which are grafting, and that minimizes the interaction. And then they could show that the interactions between two colloids are completely zero the moment they are completely separated, right? And hence they could create a hard sphere in an experimental perspective. And now once they could create, now going back to our discussion, now can this crystallize experimentally? And here what I show you is series of so these are like this dispersion, the colloid dispersed in this solvent. These are the solution, colloidal solution. Going from left to right is the direction at which the volume fraction of the colloids are increasing, right? So at the lowermost, you're starting with something like 20% volume fraction to the highermost, where you are going up to like 70% volume fraction of the colloids. And if you look at the leftmost vial, you see rather homogeneous color, right? Which indicates that like the colloids are completely dispersed in the solvent, and this is a pure liquid, right? And when you start increasing, you can see that there is a small part which is settled at the bottom of the vial, which shows like a marble-like feature, right? And this marble-like features are because of the light getting reflected at the because of the crystalline texture which is getting formed. So this is having a fluid crystal boundary. And if you keep increasing, the fraction of crystals are increasing, as is also indicated in the graph below. When you increase the volume fraction of the colloids, the fraction of crystals are increasing, and by around 40% or something, we could get completely crystal solution, right? So here, again, to remind you that like there is no interaction, and this crystallization is only possible because these colloids find more number of ways to be crystallized. This is essentially driven by entropy, right? And not only that, entropy can form this crystallization, and there are much more complex and rich ordered phases can be formed by just controlling entropy, by changing, for example, here there are different shapes of the colloids that you can change, and you can get different kind of orders. And so essentially, this is up to your dream, like what kind of particles you synthesize, and then you just try to synthesize in such a way that you remove the energetic interaction. Then entropy allows you to get the rich range of order in materials. Without going into the details, the first message that I want to convey to you is that entropy can, in principle, induce order, in contrast to the common understanding of what order and disorder are. And this ordering can happen if there are more number of ways of being crystallized than being disordered, right? And that's my message number one. And thanks to the microscopic definition of entropy, right? And that takes me to the next part of the talk, where I would like to manipulate entropies, where we can now get this this intriguing behavior of materials of the same nature dislike each other. For this, I use another epitome of soft materials, which is polymers, right? Polymers are simply plastics. These are the molecules which comprise the plastics that you see in every day, right? So many various plastic products that you see, and polymers are the molecular nature of these plastics. So polymers are long chain-like molecules which are formed by covalently linking many small molecules, right? So here, for example, I've shown you an atomistic snapshot of a polymer called polyethylene oxide. So you have one ethylene oxide moiety, and you connect another ethylene oxide moiety with a covalent bond, and you keep connecting them in a linear way that like you form a long chain-like molecule, which we call as polymer. So from a physics perspective, it is simple to think of polymers as beads which are connected via springs, right? And these beads represent the monomer moieties, are the small molecule moieties, and the springs represents the covalent bonds which are linking them, right? And at this level of polymer, there are so many local degrees of freedom which dominates the behavior of polymers. So for our simplicity, let me discuss with you today only the polymers which are electrically neutral, and the interactions between all the neighboring polymers all the neighboring monomers are screened within the size of a monomer, which essentially means that energetic interactions are completely removed. And these are not just like theoretical construct, and there are polymers which you can actually realize such a situation, be it a polystyrene or a polymethyl methacrylate, in a proper ideal solvent conditions, they don't exhibit any interactions, right? And now at this level, you can think of various degrees of freedom, like starting from fluctuation of bonds, fluctuation of the moieties, and more important degrees of freedom, like the torsional degree of freedom, for letting you realize what it means. So here I show you a snapshot of a small piece of a polymer, which just shows like 3 different bonds. And now the angle between the first 2 bonds is defined by the bond angle because of the quantum mechanical reasons, right? And now the moment you go into the third bond, so while the bond angle is fixed, and now if you think about this, a bond angle is fixed, but this can occupy any position in the entire 360 degree of this torsional freedom, right? That gives a huge entropy for this polymers. And at this level, all these different degrees of freedom essentially dominates the behavior of polymers. However, the point of concern for polymer physics is that the number of monomers comprising these polymers are often too large, right? If I just have to give you some numbers, this number of monomers can go up to like some 10,000 to lakhs to tens of lakhs, this number of monomers which is comprising a single chain, right? So in that level, the polymer exhibits a different kind of global structure, where you don't see anymore the local interactions because of the polymers, and you can define the structure of the polymer in such an aspect via measuring a simple end-to-end distance of these polymer. And now if you look at the size shape of this polymer, this rather reflects the trajectory of a simple Brownian particle, like a simple diffusion motion, where now your time is replaced by the number of monomers that you are having, right? So the shape of a polymer in equilibrium without any interaction resembles the trajectory of a Brownian particle. And hence now you can define the length of this polymer, the end-to-end distance of the polymer, via the monomer distance, which is the bond length, multiplied by the root of number of monomers, right? If it is completely stretched, you would expect this to be scaling directly with n, but because of this random walk, you have the scaling with root n, right? Root n number of monomers. And now all these monomers have this torsional degree of freedom, and hence that creates a huge entropy, and the maximization of entropy is what defines equilibrium in polymers, right? And the maximum entropy can be achieved when you have all these monomers exhibiting a Gaussian-like distribution. That is, when you just think about the end-to-end distance, and if you just look at the distribution of this monomers along the end-to-end distance, then the maximum you see is at the length where it is scaled with root n, right? And now once you have the probability, and thanks to the Gibbs entropy, we already know how to define entropy, right? So which is just probability times the logarithm of the same probability and summing over all the microstates. And now if you look at this entropy bit closely, entropy is essentially defined by the end-to-end distance of the polymer. Now if you change the end-to-end distance of the polymer, the entropy of the system will change. And at equilibrium, the system wants to have maximum entropy, and the moment you start changing the length and all those things, then the entropy changes and then system goes out of equilibrium, right? So with this basic idea, let me introduce you to a very simple experiment, right? Where now I'm going to take a substrate and attach polymers on this substrate. One of the ends is going to be attached to the substrate, and the remaining end can still perform the random walk. Right? When now these polymers are well separated, they all perform random walk, the entropy is maximized, they're all happy, right? And now let us think about increasing the density of this attachments more, right? The moment you start increasing the density, the polymers start meeting at their envelope volume, right? So then the steric repulsion, the Coulombic repulsion between the monomers start coming into picture. So then you increase the density so much that because of the repulsion, these polymers now start stretching themselves, right? And which is they're going out of equilibrium because of the way you created this system now, right? And now if you look at, for example, one way of quantifying this is by looking at the height of these brushes, these polymer brushes. And now if you increase the density of grafting or of attaching, which is what I call this as sigma here, which is the grafting density or the attaching, the adsorption density of chains. And now at very low densities where the polymers are well separated, the height is not defined by the grafting, right? It is defined by the random walk of the polymers. The moment you start, touching their, making the coils touch each other, then the height starts increasing. And at very large grafting densities, it goes almost, like linearly. And this is much more than the root n that we have seen, right? So just to bring you into our definition of polymer, this height of the brush scales with the grafting density to the power of an exponent, where the exponent is much larger than 0.5. And you can now rewrite this in terms of the number of monomers which are forming this polymer. And this height of the brush is now scaling with n to the nu, which is the exponent. And you know that this is for equilibrium, this nu would be 0.5. That's what we just discussed. And now the entropy is defined. Now what you're doing is that you're making it stretch more. The end-to-end distance is increasing further. And now your entropy is going to be changing. So this entropy of polymers in dense brush cannot perform random walk, and hence they have entropy, which is entropy of a dense brush is much lower than the entropy of polymers in equilibrium, right? And now, okay, you have created a system where just by making this polymers, getting stretched, the entropy has been manipulated. And what is the consequence of such manipulation, right? So to do that, what Khanna and Reiter in 2000 have done, and what I have been doing also, is that they have created a PDMS. PDMS is some polymer. I mean, you can create this with PDMS or polystyrene or polymethyl methacrylate. That is up to what kind of system that you look at. But what they have done is they have chosen PDMS as a model system, which is polydimethylsiloxane, and they have created a very dense brush here, which is given by this red color chains. And on top of that, they have just put this equilibrated PDMS chains where all the chains are performing random walk. And these are two exactly same molecules with exactly same chemical nature, right? So then what they have done is they have chosen a very simple system. So anyways, before going into the experiment, so here, because you are choosing the same, exactly the same polymer, there is no difference in terms of energy. You have removed the energetic interactions coming into the picture, and all that which is going to dictate the behavior of this system is the entropy, right? And to look at this system, what they have done is that they made a film, and they put at this film under an optical microscope, and which has also a hot plate, right? And they can now look at this film while things are happening. At low temperature, everything is frozen, so nothing is happening. And when you just give temperature to this system, what they have seen is that this film starts dewetting. I mean, starts forming holes and getting to retract from this polymer brush layer, right? So now here I'm just showing you a snapshot of the image, the movie where a single hole is growing. This is a nucleation is essentially a thermodynamic process. So there is no external forces needed. Just that you go to the optimum temperature where you could see these holes growing. And now materials of the same nature, PDMS is on PDMS, but the PDMS which you have put on top is running away from the PDMS on bottom, right? So that running away is what you're seeing here. This retraction of fluid of exactly the same chemical nature was quite surprising. And now we know the reason, which is entropy, right? So PDMS cannot form a very stable layer on top of PDMS because of the high entropic penalty. Now, if these coils want to interpenetrate, they have to now provide some space so that these guys can go and interpenetrate. And now, because of the high density, they cannot do that. And the entropic penalty is too high, right? And thus, by manipulating entropy, we could make materials of the same nature dislike each other. And it's not just here. We could also do it with curved surfaces, with polymer, with nanoparticles. And that's what we have done extensively, where we have used nanoparticle and then we have grafted this polymer chains, as I've indicated, via this black chains attached to this red spheres. These red spheres are nanoparticles of the sizes of ranging from the diameters are like of the order of 3 to 5 nanometer. And these chains are really long, like they are of the order of 5 nanometer or something. And so you could create such a very densely brushed system and then mix them with polymers, right? With simple polymer melt. Now, from our understanding of what we have just seen with the flat brush surfaces, we know that when the density of this brush is very low, it doesn't matter. So they just interpenetrate, because this is polystyrene. Both the grafting and the matrix are polystyrene. But the moment you increase the density of this brushes covering the nanoparticle, so then they cannot interpenetrate with the matrix, right? So then you are creating, this particle tend to aggregate, and on top of that, right at the interface between the grafting chains and the matrix chains, there exists a very deviated region, a region where you have lower density of the polymers, right? And now, what is the consequence of such lower density of the polymers at such interfaces? Then you could have viscosities at the interface, which is quite different from the viscosity surrounding, right? So if you look at the interface between the particle polymer, the viscosity there could be significantly low, even orders of magnitude low than the viscosity of the surrounding medium. And hence you could control mixing materials of exactly the same nature, viscosities and viscoelastic properties over orders of magnitude. With this, I guess I have convinced you with my message too, that the entropic penalties can make materials of same chemical nature dislike each other, which in turn may result in interviewing behavior, right? And that takes me to my next part of the talk, where with this interviewing behavior, can we now get into, so which is the focus of today's workshop, that is materials technology advancement. Can we advance the existing technologies, right? To do so, I would again still stick with polymers, and let's just remind you again that now I'm going to think about two entities, like same polymer, which is now left all by itself. Then they are performing random walk. They have a coil-like structure, and they have now given end-to-end distance. Now I take one of the ends and then start stretching it, and then make this polymer to be stretched, right? So you're removing the coil-like nature. Then what we have understood, of course, the end-to-end distance is going to increase, and not only the end-to-end distance, then that reflects on the entropy. Right, the entropy of a pure equilibrated or isolated polymer is going to be much higher than the entropy of the stretched polymer. Now, how are we going to do this? Point number one, experimentally, whether can we do it in a convincing way? To do that, we can think about a very simple experiment, right? So this is something which, so here I'm showing you a process called extrusion, which is a process which is being used to create most of the plastic products that you see every day-to-day life, right? So basically what they do is that they put in polymer pellets, this equilibrated isolated polymers into this this feed hopper, and then heat the whole tunnel and squeeze this polymers through this tunnel, so that here you get a melted liquid of polymer, and then squeeze them via the small orifice and get them out and put the different molds, and depending on the mold that what you're getting, then you can get different shapes of the products. You can, if you want tubes, pipes, plastic plates, you can get all this with this simple process. And now from a physics perspective, if you just look at the interface, right, you have a polymer melted liquid, and which is being squeezed via this small orifice, right? And that is going to exhibit shear on polymers. These polymers are going to experience shear because of the change in dimensions from your right to the left. So you're having this focusing thing, and right at the confluence area, you see this polymer start getting stretched, right? Now, when it comes out, if you can control the rate at which the polymers are getting pushed, so then you can completely stretch all the polymers. And this is something which is experimentally possible and easy, right? And now the shear, as I just said, the shear at the focus area stretches the polymer, And as we just discussed in the last slide, stretching reduce the entropy of polymers, right? So what will be the consequence of such reduced entropy? So to do that, we just performed a very simple experiment where we now got this stretched polymers and made a bundle of stretched polymers and formed a fiber, which I have shown you here, right? And with that fiber, I've attached a load, which is like, 50 folds heavier than the fiber itself, right? And now I've attached a load and I'm just going to sit and wait and watch, right? And from your intuitive understanding, from the mechanical behavior of materials in equilibrium, what you have been learned this process as creep process, which essentially this load, because it's so heavy that it starts elongating the fiber and the fiber becomes more and more lengthier, right? And that's what your equilibrium has taught you. And now you see that without giving any additional force from outside, this fiber, because they are all stretched, can now pull loads which are much, much heavier than the fibers themselves, right? So how do we understand this? Again, think about the entropy that we have defined. And this entropy is based on the end-to-end distance of the polymer. Now, because you have stretched all the polymers, and this now, if you just get a free energy out of it, then you know that like you can get some, say, just a first order differentiation of entropy, then you get something of the form of minus some constant times the end-to-end distance, which you may remember to be of the same form as the simple harmonic motion, right? So that the force is increasing negative to the spring constant and the distance between this from the center to the object that you're keeping, right? And now what we have is this, because of the stretching of the polymer, and this polymer can now act as a spring and pull these fibers, and this spring constant is defined by temperature, which is essentially entropy, and hence people call polymers rubbers as entropic springs, right? Not only this, and now one can counteract this pulling of the load with again some additional heat, and then make it to again extend, pull, extend, and oscillate in real time. This has been shown very nicely with by the MIT group, where you could see now all this polymer helical polymer fibers, they have attached a load with respect with that fiber. Again, the load is much heavier than the fibers, and when the heat is on, then they pull, because the entropy wants to now when the heat is off, they want to pull, because that's what the creep says. And when the heat is on, then they want to relax the entropy and then again pull the load back. So now you can see that this oscillates in real time, and just by manipulating entropy. And this is a technology that people are trying to now get into, like, even biological systems, like where people are thinking about artificial muscle fibers and so on. And also from another perspective, where one can control the optical properties and electrical properties by just controlling the length of the chains, and which in turn is what we are using to control the entropy of these polymer chains. So with that, I come to my third message, where hope I've shown you that like controlling the entropy could in principle yield interesting and novel material behavior, which could give rise to new advancements in material technology, right? So with that, I come to the conclusion of my talk, where I say entropy can in principle induce order and crystallization, and make materials of exactly the same nature but dislike each other, and also create novel properties, right? So before ending the talk, I'm just showing you just what we have proposed with simple polymers, that with maximum entropy, that is with equilibrium, we may only have started understanding the tip of the icebergs, and there is so much to yet understand about the reduced entropy of these polymers and what are the different manifestations that it can make. And for those who are interested, here I've given you the link for the perspective that we wrote. And with that, I thank you all for your patience.
So thank you, sir.
Thank you, sir. Thank you very much.
Thanks, sir.
Thank you.
Informative session, sir. This is time for question and answer. Then the participants posting some questions. I have pasted it in Word. Can I share it, sir, now?
Yeah, that would be good.
Thank you. Thank you.
Should I stop sharing?
Yes, sir. Murugan sir, you share பண்றீங்களா? Please.
Is it visible, sir?
Yeah. Okay, so what was the entropy in free space? If the value comes negative, what was the symmetry of free space? I'm afraid that I don't understand the question. Maybe if the person who asked the question, if he's online, then maybe he can ask me the question.
I think so. They are in YouTube, sir.
Okay.
So all basic electronic related virtual labs are available. So all virtual labs are available. So for example, if you want to do the VI characteristics of diode, you can just click on it and you can do the experimentation. So these are all. This is all about what is the vlab.co.in. Now, by using this vlab website, now I'm going to explain how the Meldes experiment is going to be operated.
Sorry, what is happening here?
Going to do. Yeah, I'll explain now how to do the Meldes experiment now. So yeah, I'm going to VLab.
Sorry, I'm not understanding what was spoken. The audio was not so good.
Sir, Murugan sir.
Sir,
Go to the second question, sir.
Go for sharing, sir.
Amrita is some part of VLab where they have developed all physical science related.
So can we switch off the other mic? I mean,
Now, in my today lecture, I'm going to explain the Meldes experiment.
whose lecture is going on? Somebody is going on.
Participants, if you want to ask question, you unmute yourself. One by one, I ask your doubt.
Sir, can I ask? I'm Dr. Chitra from
Okay,
Kutralam.
go ahead, ma'am. Go ahead, ma'am.
In the third point, in the entropy in materials for normal behavior, he was explaining about the length of end-to-end length. Sir, are you hearing? Can you hear, sir? Sir, can you hear?
Your mic is muted, sir. Please unmute it, sir. Siva Surendra, sir. So your mic is muted. So you have to unmute your mic, sir.
Hello, can you hear?
It's audible, ma'am. Yes.
Yeah. So now, do you hear me?
Yes,
Sir,
sir, yes.
excuse me. One
Yeah.
small
Go
doubt.
ahead. Yes.
In the third point, entropy in materials for novel behavior, you were explaining.
Yes.
But the end-to-end length in the with the curled behavior of polymer and the
Yes.
stretched one,
Yes.
that REE is lesser than R, this
Yes.
length. How same length only, no, sir. The stretching is same length only. No, how the length varies, entropy varies. I can understand, but the length remains the same only, no, sir.
Okay, so that's a good question. So there are many length scales in polymer, right? What we are speaking is about the mean length that a polymer adopts itself when there are no energetic interactions, right? And that is not a completely stretched conformation, right? If you think when you completely stretch, then of course all the distances are defined by the bond length, and you're not changing the length of the polymer in that sense. But if you now think about all this coiled conformation where there are enough spaces, and hence the end-to-end distance of these coils, right? That depends on what kind of forces that these polymers experience, right? And now when you stretch this, the fiber is formed where all these polymers are stretched, right? So then of course, if you think about, yeah, I don't know which one I'd say, but think about just take a wire and then, like just coil itself, and that's how it is with maximum entropy. And now when you stretch it, you can still stretch the coils. That's what I'm speaking about, the change in length of the polymer.
Yeah, I can understand. I can understand, sir. Very nice presentation. Thank you so much, sir.
Thank you.
Thank you. Very interesting. Very interesting.
Sir, another question. What's the relation between Gibbs free energy and entropy?
Well, you have this energy minus temperature times the entropy. And now whether you're using Gibbs or not, that will only change whether you have U or U plus PV, right? So, but the entropy is always there in the negative part. Was that clear?
Sir, raise that.
So I maybe go to the second question which was asked. So in the sharing screen. So what are you referring to disliking in materials? Is it just the bonding? So no, we are not speaking about any chemical bonding here. We are only speaking about the interaction between, the van der Waals interaction between these chains by themselves, right? You are not changing the bonding. All the chemical nature is fixed. The only thing that you are changing is a physical interaction. Now, if these polymers, with the brush, if these polymers want to interact, right? So then they have to interpenetrate. They have to go in and then mix with each other, right? And now you're stopping them from mixing by increasing the entropy of these chains which are stretched. Because they are stretched, there is no more space for these guys, this coil-like polymers, to interpenetrate with themselves. And that is what we call as disliking of the same kind of materials. Right? If you put water on top of water, you would have expected them to be completely, mixing well. And now you're putting polymer on the same polymer, but they are not mixing well. Now, when you are changing the entropy, right? That is what we called as disliking in the materials. And now question number 4, can only PEO polymer exhibit this property? No, any polymer which, any ideal polymer, which all the interactions are screened within the size of the polymer. And that is what is the case for most plastic products that you see, be it styrofoam, that which comes along with all the packing of your objects. And, this kind of styrofoam plastic plates that now the hotels are using to make this food packages. And, think about other polymers. The polymers which forms the outer case of the wirings, anything which comes to your mind. So any polymer, in principle, if you can play with the entropy, can show such properties that what I was showing. And then, can biomaterials be made into polymers? There are a lot of biopolymers, right? We all are having proteins. Proteins are, one epitomic case of a biopolymer, right? And all this proteins and all these biopolymers have an additional thing where there is also an interaction which comes into play. This monomer starts interacting with themselves, right? And now on top of entropy, you also have interaction. But there are various cases where it has been shown. For example, if you have a cell wall, and now a protein wants to go into the cell wall. For example, that's how RNA becomes DNA, and that's how the genetic information is stored in cell. So now it has to go through the cell wall, and that is like via small pores, right? And there, this coil-like polymers have to get stretched themselves while penetrating themselves into the small pore diameters, right? So this is possible with every polymer that you may think of. Right? And in biology also, entropy plays a very important role, especially in terms of transport, right? And the next question, how the interaction of polymer with nanoparticles, do viscosity increase or decrease? So that is what I told you. You can achieve both the cases, right? You can make it to increase, or you can let it decrease. Now, if you have a nanoparticle where you have now attached this polymers, and this is like, for example, since I was showing, so this was based on my work, where we have used nanoparticles to be gold, and we have used polystyrene to graft them, right? These polystyrene are ended with this thiol group, and then this is a simple physical adsorption, right? Because thiol has a higher Amakar constant with the gold, so they can just get it completely attached. And now, depending on the density at which these chains are getting attached, you can change the grafting density. And now, by changing the grafting density, we know that the polymers can either stay in coil-like form or can get completely stretched. When they are in coil-like form, when you mix them with other polymers, they can get interpenetrated. And now if they are not in coil-like form and if it is completely stretched, then because of the entropic penalty, this cannot interpenetrate with the polymer matrix, right? And that creates a de-wetting region or a reduced density region around this particle polymer interfaces. And that enhances the mobility at the interface, hence decrease the viscosity of this whole system. So you can choose the density, grafting density, and then change the viscosity to increase or decrease.
So if any other interested, you can ask your question by unmute your mic. Any other interested? Okay, thank you all. Then I'll invite Dr. Anandi ma'am to say a vote of thanks.
Sir, thank you. Thank you, Surendra. There is no more question. I think we can end up the session. Respected and our most distinguished chief guest of today's session, Dr. Shiva Surendra. Gives me an immense pleasure to give the vote of thanks. First of all, I thank all the professors from various colleges and students who is giving us a resounding success. Your presentation is excellent, and Shiva Surendra, it's wonderful to have a band knowledge about entropy. So we all know what entropy we defined as it is a disorderliness, a statement, but now we can understand what is entropy, and you have given a detailed thing. Thank you. I thank you once again for your presence today and for your readily acceptance for gracing today's workshop. And I thank all the participants for your overwhelming response for making this first day of our workshop a grand success. I think you can share your mail ID, Shiva, so that they can ask any doubt if they have. Through mail, they can contact you. Thank you.
Sure, I'll just put it in the chat. So.
Oh, sure.
Thank you, sir.
Okay.
Murugeshan, sir, please share the feedback link in the YouTube, sir. I'm not able to share it. Please share it, sir, now.
Thank you, sir. Dr. Shiva Surendra, thank you very much.
Thank you. So I'll thank you. See you.
Thank you, sir.
Thank you.
Anandi ma'am, thank you.
Yes, sir. Thank you, sir.
Thanks, sir. Anita ma'am, thanks a lot.
Thank you, sir. Thank you.
Can we leave, sir?
Yes,
Can
ma'am.
leave? Finish.
Yes, sir.
Without unmute, I talked, I think. Okay, then this is the time to end up our session. And then tomorrow, I will meet tomorrow for next session actually. Then thank you all the participants and speaker. And then we'll meet you tomorrow.
Thank you. Thank you, sir. Thank you.
Thank you.